Okay. So I'm disorganized as usual, or maybe disorganized in a slightly different way than usual, but definitely disorganized. I guess one question is whether you have things that you want to say right now. I have things that I want to say. Well, they're very disorganized. So let me start listing topics, and you can list topics that you might want to talk about too, if you have any. I mean, okay, so if I were, following in a sensible order, then I'd be following from last time, and it would be something like special commutative Frobenius algebras as a tool applied to the study of, as a tool in understanding reciprocity theorems for abelian torsors or something. So that's definitely still on the list of things that I'm thinking about, but it's not necessarily what I'm going to talk about today. Reciprocity theorems. What do they say for abelian torsors? To the extent that that makes sense, it sort of makes sense. So the second topic is, I guess, sort of in the nature of a word from the sponsor. The sponsor in this case being the special commutative Frobenius algebras. Word from sponsor. The sponsor being the special commutative Frobenius algebras. In other words, I have a whole bunch of very naive questions to ask you about not just these special commutative Frobenius algebras, right? Maybe I should really say Frobenius algebras or something like that. So, sort of backing up or enlarging the perspective and asking you questions about Frobenius algebras, because, right, in a way, it's very evident, even just from the terminology, that we're doing something, we're not taking full advantage of the latitude of the concept of Frobenius algebra. These are very special ones. And in some sense, what's very special about them is that they're very discrete in a geometric viewpoint. Or maybe discrete and compact or something, meaning essentially finite discrete or something like that. So that's a big hint that there's more to this than that. And but on the other hand, well, so what am I trying to say? So I mean, there's all sorts of different directions that you can generalize things here. I'm not even sure generalize is the right way, but it has to do with going beyond what I've been talking about. I mean, these special commutative Frobenius algebras, which are geometrically very discrete finite things, it's not just that that's failing to take advantage of the full latitude of the Frobenius algebra concept. It's also failing to take advantage of the full latitude of the whole concept of algebraic geometry within which we're applying the Frobenius algebra concept, because algebraic geometry is about way more than just discrete stuff. Algebraic geometry is obviously about algebraic varieties, which have very continuous variation. Now there is some interplay and confusion here between I guess this is sort of the famous sheaf theory joke that, sheaf theory is the subject where you do topology horizontally and you do algebra vertically. So the algebra is more discrete and the topology is more continuous. So there's this tendency to have situations where the base space is continuous and the fiber is discrete. Of course, that should be distinguished from other situations where there's an opposite tendency. There's a tendency for the base space to be more discrete. Well, I'll have to think about that. But that's some different game. So yeah, I'm being very conscious of the fact that there are lots of ways in which what I'm doing here when I'm studying the reciprocity theorems for abelian torsors, I'm very conscious of the fact that I'm trying to be very conscious of the fact that that's a very narrow viewpoint in a way. And so there are much wider things to look at. So like I say, well, one way that it gets wider is that, the reciprocity theorems are kind of part of Galois theory, and Galois theory could be considered part of the, I'm not sure if this is the right way to say it, but maybe you could sort of consider it as part of the theory of motives if you take a sort of semi-modern perspective. But when you think of Galois theory as part of the theory of motives, which, and I'm going here by things you've told me, and I only have vague ideas really about how motives work. But from what you told me, when you think of how Galois theory fits into motives, it's just like, in some sense, the zero-dimensional part. In some sense, it's almost like the discrete finite part or something of the theory of motives, maybe. So I'm very conscious of that way in which this is a very narrow perspective. But this other idea of examining the concept of Frobenius algebras in a more general context, where they're not necessarily special or commutative or whatever, that seems to be going in a rather different direction. I'm not sure what the relationship is between those two different directions, but anyway. So that is the that is in the nature of what this second topic is about. It's about asking a bunch of very naive questions about Frobenius algebras, and I mean, it's looking in a more general context, but it's very provoked by these questions. These naive questions that I have are provoked by things that I've been trying to do, applying Frobenius algebras in the context of these reciprocity theorems for abelian torsors. So that's a little bit of indication what the second topic is about. And the fact that I wrote less about it, but said more about it, means that probably suggests that might be what I'm going to talk about today. But nevertheless, I'm going to write down the third topic, which is a topic that I haven't been getting to, and that is the belief method. So this is something you brought up, very interesting question. I mean, you probably have an answer to the question by now. You probably have multiple answers to the questions.
No, I don't. No, I don't.
Well, okay, then maybe I don't know. You could talk me into talking about this, but the belief method for, I guess, let's say, relationship. Well, I'll say it's for this homomorphism of affine algebraic groups. So let me think about that. No, sorry, affine algebraic monoids. So don't tell me, let me think about which direction it goes. So it's like you can have, right, invertible matrices is like a subset of more general matrices. So from a sort of naive point of view, it's like GL2 mapping probably as injectively in some sense, or monically or something like that, into, maybe we just call it M2, and the M probably doesn't stand for monoid, it probably stands for matrices or something like that.
Yeah.
And so yeah, it's just, that's supposed to mean the 2x2 matrices. I'm just calling it M2 at the moment. And so let me just think about this for a second. So when you apply the belief method to this, let me think about what that means. Well, I'm really just trying to straighten out the variance here. So the idea is that, these are two rigs. Well, these start out as affine algebraic monoids.
Mm-hmm.
But by taking the comodule categories, you get two rigs from them. And by the way, I guess since you prefer those, well, I shouldn't accuse you of it, but I can definitely accuse Todd of preferring the absolute two rigs. Maybe I could accuse you of that too. But when you do the absolute two rigs, you don't want to take all the comodules. You just want to take, what is it? Is there a concept of finitely generated comodule? Is that what gives you?
Like finitely generated projective modules, I think maybe.
Well, but it's comodules, right?
Well, okay, sorry. I don't usually think about it this way, but I just know that, like, if you think about modules of an algebra, you could start with the algebra as a module of itself. And then if you take the Cauchy completion of that, you're throwing in all the finitely generated projective modules. And so it's not just
we're talking about the comodules. What?
Yeah. So I'm just saying finite generation is not enough.
Well, but I wasn't even sure, maybe it's easier in the comodule case. Maybe you do just have to take, I don't even know what finite generated means for a comodule, but maybe it does mean something. But anyway, you do need some restriction, presumably, because if you just take all the comodules, you're getting this absolute two rig.
Yeah.
One way or another, you're getting two rigs here by taking the comodules. And then I think of those two rigs as being theories. And, so it's like the theory of a GL2 torser, which is basically, morally a synonym for, a GL2 torser is morally the same thing as a two-dimensional vector space. And, since we're working in this affine algebraic doctrinal or doctrinaire context, you don't even have to try to decide what field you're working over. It actually makes sense that you just, talk about vector spaces without having to think about whether they live over some particular field. DL2 torser is, in some sense, synonymous with, morally synonymous with two-dimensional vector space. But then what is an M2 torser? What is that like? I guess you and I have talked about that, and it's sort of like a sub two-dimensional vector space.
Yeah.
Although maybe we should call it quotient two-dimensional vector space or something like that. But so let's see. So the thing I'm agonizing over at the moment is which one is more skeptical and which one is more gullible. So don't tell me the answer yet. Let me think about it. So, is it the, maybe it is naively obvious, right? So but naively, you would think that a two-dimensional vector space is a sub two-dimensional one with an extra property, namely that it's strictly. So that would mean that that the direction that the gradient goes like this. That you have to add some extra belief to the skeptics to get the more gullible things. Yeah, so that's a question we've been thinking about, but we haven't been talking about it that much, but it's a possible thing to talk about. And you could force me to try to talk about that right now, but it feels like I'm going to start talking about asking you my naive questions about Frobenius algebras, and it's going to be equally disorganized either way. So I don't know. Do you have any, or do you want to talk about something completely different?
I really want to get these damn reciprocity theorems. You're threatening to come you're coming very close to that last time, and then threatening to like
yes
do it even better next time, and now you seem to have veered away.
Well, okay, I talked. So one of the problems I'm having now is that we've been meeting on Thursdays instead of on sorry, we had been meeting on Thursdays, and now all of a sudden we're meeting on Mondays, which, so I like this. I like this thing I do where I have very freewheeling discussions with my friend Simon, where we make ridiculous mistakes way more than when I talk to you. I mean, I make ridiculous mistakes when I talk to you, but even more when I talk to Simon. I think I was happy when I was, I'm more like on Mondays I would talk to Simon, and then Thursdays I would talk to, and now I'm doing it backwards. So like what happened last week was I talked to you on Monday, I guess. And then it wasn't until Tuesday or something that I talked to Simon. And boy, did I discover, huge mistakes that I had been making. So that's making me hesitate to talk. Well, I mean, I guess the point is
start thinking of Monday as after someday instead of before. You can do it. I can
do that. I'm not sure that's possible.
It's possible. You're not bound by the calendar.
Well, all right, I'll think about that. Right. But I think what happened is that when I was thinking about the reciprocity theorems, I really ran into things that were confusing me, and it really forced me to take a more wider perspective about the Frobenius algebras, or it really encouraged me. So,
well, okay. It sounds like you definitely want to talk. Well, no, yeah, you definitely want to talk about two. So let's do it. But I'm just saying that, like, it's been a long time when I've been thinking we're like slowly.
Well, I'm learning huge amounts of things. I'm just not teaching huge amounts of things, but I'm really, really learning a lot about this stuff. This almost seems, have I mentioned this almost seems like a role reversal from the old days when, it always seemed like, we were trying to teach each other and learn from each other, but it always seemed to be that, I was teaching you and you were learning from me, and it never worked the other way. And now it seems to be the reverse of that.
I don't know, maybe you're learning a lot of things, but I'm not. What am I teaching you? I didn't know I was teaching you anything. I thought you're just learning stuff.
Well, what's that word I'm looking for? Just kind of osmosis or something like that.
Okay, yeah. No, it is true that I noticed you start talking about special commutative Frobenius algebras and about growth and Galois theory, and descent and things like that. Yeah. So those are things I ran off and learned about because I was interested in stuff you were saying and wanting to like learn what other in a very general way, and I was wanting to learn what like growth and had to say about this stuff. Yes.
Well, that is I mean, in a way, that is sort of supposed to be the way our collaboration is supposed to work. Kind of bouncing back and forth. I didn't realize I was only watching the bounce from my end. I didn't realize it was bouncing back at your end as well. So
I don't want to talk about anything, but I'll list a couple of things that I could talk about.
Okay,
If
one thing I just want to emphasize. I just want to emphasize that you really could force me to talk about three. You really could, but you don't have to. But go ahead. What were you going to say?
I would only want to talk about three if you actually answered my question, and I haven't.
No. I'm still working on it. It's very fun.
Yeah.
I think it's more fun to work on it than to get the answer. But you apparently want.
I just want to know the answer. I don't care about
it. Okay.
So anyway, one thing that I really don't want to talk about now, but it's a lot of fun to talk about, is I've been starting to study tuning systems in music.
Oh, sure.
And thinking mainly about Pythagorean tuning, first of all, more carefully than I had before, and then what's called just intonation, where you have very simple fractions. Pythagorean has fractions that are just built out of 2s and 3s, but they get rather elaborate. And just lets you do 2, 3, and 5.
Sorry. Yeah, I'm imagining it goes 24, 27, 30, 32, 36, 40, 45, and then, just double the octave. So it's like,
I can't even remember it that way, but that's
F, G, right. A, B, C. I mean, look, you got a perfect 4, 5, 6 right there. You've got a, so the major thing is perfect. The dominant thing is perfect, right? 36, 45, 54. That's a 4, 5, 6. Yeah. So those are perfect. What about subdominant? Is that a perfect thing? 32,
I don't think so.
40, and 48. Is that a 4, 5, 6? I guess that's right. So it's kind of like major and subdominant and dominant are all perfect 4, 5, 6s or something like that. Yeah.
I'll just show you some. I'll share my screen. I think.
I'm sorry if I forced you to talk about it, but go ahead. Yeah.
Well, I know I didn't want to talk about it, but anyway, now that you've done it,
and I don't have to turn off my screen sharing. You're just going to steal it, right?
I was tempting to.
Okay. Well, I can turn it off.
Sorry. Yeah. So here, this is the way. This is something that made it click for me a bit. This thing here. So this is like in C major.
Yeah, that's where we've got it right there. That's that's right. That's right. I just wasn't emphasizing the fact, right? What you're pointing out here is that, I said something like
yeah, you said subdominant,
tonic, dominant, and subdominant. But now it's like you're trying to give a different interpretation of what sub means in subdominant.
Yeah.
That, it's like the reciprocal of dominant or something like that.
Well, that is.
What?
I mean, that is sort of true. They call the 6th the submediant and the 3rd the mediant. And it's not like the 6 is like directly below the 3rd. It's like the reciprocal of the 3rd.
So you're telling me that I've actually been misetymologizing it all this time?
Well, I think for subdominant, everyone likes to etymologize it that way, so that it's sort of like almost become correct. But
I mean, and again, but this reciprocal relationship that we're talking about, it already suggests all sorts of ideas about how modulation should work and things like that. When you switch to the dominant, the original thing is now the subdominant.
Right. That's another reason why it's called subdominant.
Well, that should be called the anti-dominant or something like that.
Yeah. Well,
it's
like dominant.
Inverse dominant. Yeah.
Yeah. Right. Exactly. Yeah. Anyway.
Sorry.
So we won't talk about that.
Okay.
We'll
but you only mentioned 2 so far. Pythagorean, we could mention the other one.
No, that was
I mean, there's all sorts of ones. What is well-tempered? That's neither of these, is it?
There's no specific one well-tempered thing, and nobody knows what Bach was using for his.
Okay, fair enough. But there is the horrible or very useful. What do we call it? The
equal tempered.
Equal temperament. Okay.
Yeah. So I just take that.
And then there's zillions of others, but those. Okay.
So it turns out though that the 2, 3, 5 stuff, it can be, those fractions can be used for things other than just intonation. And so anyway, the reason why I got especially interested in this, I was getting interested in it, but it turns out that Newton wrote a paper about tuning systems that he never finished, which exists. And there's a,
You said it does exist. That's what you said.
like the fragmentary manuscript is available.
Yes.
And there's a really nice paper about Newton's work, comparing it to other things at the time, and it's just really lots of fun. So I'm trying to gear up towards understanding that by making sure I really understand Pythagorean and just intonation. This guy Mercator, who's not the Mercator. I hadn't known there were like two guys named Mercator. There's a guy named Mercator who came up with a power series for the logarithm. And then there's, of course, the famous map Mercator. But logarithm. I don't know, actually.
Okay.
The logarithm Mercator guy.
What kind of name is that? Is that a Latin name, Mercator?
Yeah, I don't know. It sounds Latin. Yeah.
Okay.
So anyway, that guy also worked on music theory and may have influenced Newton.
Okay.
So anyway,
let me write that down.
If I ever talk about this stuff, you'll see why it's so cool. But I don't want to talk about it.
Okay. So I mean, the Pythagorean tuning system is a very circle of fifths-ish.
Right. Yeah.
The just thing is just a little bit arc of fifths, just this little arc of the, and it's kind of a trade-off.
Yeah. It's a very different thing.
Just this 3-point arc.
Yeah. So I guess another way to put it, another thing I'm sort of wanting to do is just sort of understand a bit about the tuning systems that were actually most used in like medieval and Renaissance and Baroque music. So Bach was right around when they started trying to come up with better ways of tempering the just intonation to make it easier to change keys without sounding loud.
But so do people argue about whether, what was his intent? Was his intent, I mean,
people seem to think, people generally think his intent.
I mean, was his intent to take advantage of the fact that they weren't all the same? Probably yes, but
not mainly
versus taking advantage of the fact that they were all the same.
I think they were taking advantage of the fact that in a well-tempered system, you can play in all keys and have it sound pretty good. Compared to just intonation, where if you try to play in some of those keys, sounds really pretty bad. That is like the fifth sounds really parlous, really. So people had just been inventing these so tempering means fixing just intonation to make it more easy to play in different keys. That's what tempering actually means. And so there are a number of, so he was probably trying to show off that on a new tempered tuning of a keyboard, you could play all these different pieces of his that he wrote in different keys. And so some people thought he was using equal temperament, but that basically most scholars don't think that he was using equal temperament. It just wasn't really around at the time. And so they would sound different. So it was also sort of maybe showing off the individual character of the different keys, but they were all.
But that would be interesting if you could find in the music that he wrote that there really was something that made those good for those particular.
Yeah, I was just thinking about that recently. So people are like really desperate to try to figure out what he was thinking, and they've gotten to the point where there's this on the manuscript that he wrote of the well-tempered clavier. There's a doodle on the front page, a very doodle full of curly cues, and people have tried to interpret that doodle as like a a cryptic description of the tuning system that he was using.
Yeah.
But it's really grasping at straws, because even if you believe that's true, it's really not so easy to interpret it that way. So people would love to do that. And I was thinking, well, why don't they just like try to figure out, which of the tempered systems it might have been that would make that stuff sound the best. But haven't seen any. Someone must have tried doing that, but I haven't seen anything about that. And of course, that could be not so easy to decide either. But yeah. So yeah.
Boy, I'm just noticing here. Is what is it? Is it? Do they say A is 440? Is that what they say?
Nowadays.
So that means you just multiply all these numbers I wrote by 11. It's funny that there's just.
Can you share your screen again?
Yeah.
Yeah, I never remembered those numbers, although now I remember you telling me about those numbers a long time ago.
And it looks like, you're talking about bad fifths. It looks like
you're not sharing your screen. You're not really showing.
Oh, okay. Sorry. Maybe I did it wrong. Let me try that again. I was sharing the wrong screen. Okay.
Yeah.
Okay. So, yeah, you just multiply these numbers by 11.
I see.
So D to A looks like the bad fifth. It's
I think
297 to 440. In other words, it's 27 to 40. And that just doesn't seem, that's a peculiar approximation to 2 to the 3, 2/3 or whatever. 2740. This is a peculiar approximation to 2/3.
Yeah.
So I think that might be the weird one.
Yeah, they call that the wolf fifth.
Really?
Because it's supposed to howl like a wolf.
I guess you must be right about that, but maybe I should look it up to just make sure I'm believing what you're saying.
I mean, they're different wolf. There are different things that people have called the wolf fifth. Here, I'll play you a wolf fifth on.
Isn't there a person named Wolf, Tom? I don't know, but go ahead. Yeah.
So here's a wolf fifth. Oh, this isn't in just intonation. This isn't some.
Okay.
I don't know what one this is, but anyway, here, I'll play you a wolf fifth. I'm confused.
I mean, some people consider a tritone rather wolfish, but I don't know.
That's supposed to sound bad.
Yeah.
Can you hear that?
Oh, no, I couldn't hear.
Oh,
I've heard that. Okay. Say it again.
Yeah, that's it. Anyway, never mind. Let's quit.
Okay.
So, anyway, and also a thing I'm really interested in now, because someone's finally teaching me something about it, is representations of the symmetric group on fields of characteristic P.
Well, that could also be really interesting to things we've been talking about.
Yeah, it should. Just some basic stuff.
Yeah, in some sense, we really should get into that. But of course,
right.
Well, I was going to say that, of course, I want to take a ridiculous belief method focused approach to that, but I'll have to think about that. I've certainly thought about it, but I'll have to think about it more. Okay, let me just write that down.
It's related to the thing you were starting to talk about last time, about how you can't always divide, you want to divide by 2 to get some food. Yeah, so it's just that kind of.
That's definitely true. That's very much true. But I'm just trying to think of how to write it down. So maybe it's called. So some people just call it modular representations. Is that right?
Yeah.
Which does that conflict with all sorts of other terminology?
Yeah. You could look at modular representations of the modular group, I guess.
Modular representations of n back.
Yeah.
Okay. And that's okay. So I'll try to I'll try to say something now.
Okay.
So okay. So I'm thinking about Frobenius algebra concepts. I guess one of the things that provoked me here to start thinking about this. Well, I realize that there are so many things that I get confused about. So I mean, one very specific question that I get confused about, but you shouldn't tell me the answer to this yet. And because the question probably isn't properly phrased to have a good answer yet. But I've been getting mixed up about, in what contexts for various different flavors of things that might be called Frobenius algebras, in all those different contexts, when does it happen that you get a pairing or a co-pairing, or both a pairing and a co-pairing, and that they are, inverse to each other, or non-degenerate. And I've been finding myself getting confused about this. So that's sort of one of the motivating questions that I have about this. But somehow what it led me to think about is, I mean, so for example, we have this idea that, let me see if I can get this right, that if you think about the prop for special commutative Frobenius tensor monoids or algebras or whatever you call them. If you think about, in other words, if you think about the special commutative Frobenius prop, then we have the idea that syntactically it's co-spans, if I remember correctly.
Right.
And the extra special ones would be corelations, according to the, if I remember correctly, that little chart that you wrote down. We don't even have to check that right now.
No, it's right. It's right. It's right.
Okay, I'm probably not even that interested in the extra special ones, although we may, I may actually ask about them too. On the other hand, if you look at some kind of less special commutative Frobenius algebras, or perhaps even not necessarily that commutative Frobenius algebras, then in at least some cases you still have a prop interpretation, although in some cases that prop concept might begin to get categorified if you're looking at categorified Frobenius algebras or something like that. But I'm not focusing on that yet. But I guess you must have thought about that a bunch.
Some point.
Okay.
Not so much lately, but yeah.
Okay, fair enough. Me neither. And yeah, that's not the main thing I'm aiming at today. So we've got well, right. So in many cases we still have a prop interpretation, and so you can ask about what I'm calling the syntactic viewpoint towards this prop. It's just kind of like getting a very syntactically global, concrete picture of what all the operations in the prop look like. So like we said, in the special commutative case, it was the co-spans. Allegedly in the extra special case, which I'm not completely clear on what that's good for, but it's apparently just the corelations.
Those, by the way, are sort of like those are like invertible objects that are
well, I was thinking about that. I was thinking about that, but okay. I'm sorry. Okay, that suddenly
it could be really interesting, but they're not many classical.
Oh, wait a minute. Wait a minute. Let me think. Oh boy, but there's something weird about that. It sounds like at first I was thinking, oh, it was really stupid for me not to have thought about that, but
What?
Something very weird about this. I'll say my stupid, naive confusion. So there's this idea of, and there is this idea of an invertible object under tensor problem. But
yeah.
Well, there are okay. I mean, they're right. There are these games about how the morphisms between special commutative Frobenius algebras. There are different kinds of morphisms that you can look at. You can just look at the, homomorphisms of the prop algebras. Or not even sure homomorphism is exactly the right word. You might try to call them homobimorphisms or something like that, because they're preserving the operations and the co-operations or something like that. But those tend to give now sometimes you gave me the impression that they were just mainly giving the isomorphism, but it seems like they might give the injections between the finite sets. If you think of these special commutative Frobenius algebras as being honorary or moral finite sets, then
no, I think they give the bijection, the isomorphisms, because you can, for any Frobenius algebra homomorphism or homobimorphism, you can construct an inverse using the caps and cups that you have available. You can turn around the
funny.
morphism.
That's funny because, well, okay, that could be very interesting. Let me write that down. So okay, this is I'm just writing this down. You can, I still have stuff visible, right? I'm taking notes here as I'm talking, as I'm actually, as you're talking, as I'm getting answers from you. So this is, I'm writing this down on the general heading of Frobenius props. Okay, and so, yeah, you're already telling me all sorts of things here. See, all right, so one of the things you're telling me, see, I had been, okay, what kind of logic is this? Let's see. So I mean, in Grothendieck's geometric doctrine, the doctrine of Grothendieck toposes and geometric morphisms between them. There's a concept. There's a thing called the theory of a decidable set. And I think it might sometimes be called the Shanuel topos or something like that. And it just kind of presheaths on the category of sets and injections or something like that. So, I mean, for a general object in a topos, you can talk about equality, but you can't talk about inequality. Or well, I guess you can talk about inequality, but it's some sort of weird non-Boolean complementation of equality. But if you want a Boolean complement of equality, then you have to go to this Shanuel topos. And I was sort of conjecturing that was related to this Frobenius algebra. What am I trying to say here? What am I trying to say? Okay, first of all, let me write down what you said. So you said that any special commutative Frobenius tensor monoid, I'll call it a homomorphism for the moment. But there's an issue about what that means. Any special commutative Frobenius tensor monoid homomorphism let me say for any special commutative Frobenius, you can build an inverse using cup and cap. I'm going to put cup and cap in quotation marks too, because that's also part of what I'm not clear on. So so that's a very interesting idea. But on the other hand, that doesn't mean that you can't get hold of more general maps between these moral finite sets. It just means that you have to get a hold of them in some different way. Like, for example, just taking homomorphisms between the underlying commutative algebras.
Yeah, that gives you. That's
the maps.
That's the one that makes people call them separable algebras. That is, with that, one of these things where the correct notion of morphism is just the algebra homomorphism, or
it sounds like what you're saying is that you right. This also depends on how your terminology works for what you think of as the difference between a property and a structure. It sounds like you want to think of separability as a property in the sense that the morphisms are not required to preserve the extra operations.
Right.
So it's just kind of that those operations exist. And exist again, different terminologies about what existence means. But whereas you want to think of special commutative Frobenius as this sort of structure version. So you're distinguishing between them. I mean, and to me at first, I wasn't sure what you were talking about, or maybe I didn't like what you're talking about, because, I don't like the idea. I usually don't like the idea. Not sure how hard it would be for me to get used to it, but the idea of, right, you're kind of like putting into the name of the object something that's really about the morphisms or something like that. I mean, again, a lot of people think, well, that's the whole idea of category theory, but but again, that's partially why I'm sort of almost more of a groupoid theorist than a category theorist. Let's see.
The only reason why I'm using this terminology this way is because it does seem to match what most people use. So people get the least confused if one.
Sure. Nevertheless, let me just write down this vague idea here that separability, separable commutative tensor monoid is to special commutative Frobenius tensor monoid as property is to structure. Right. I mean, one of the reasons why I'm still not sure how much I like this is because I think of special commutative Frobenius sometimes as being a property. Now I have to think about in what generality can you really think of it as being a property? And again, it depends on what you mean by a property. But I just want to write down that this is your viewpoint about it. When I call it your viewpoint, I mean it's sort of one of these things where you're being don't tell me, it's like the difference between the two kinds of dictionaries, the prescriptive versus the descriptive. So you're being more of a descriptive linguist here and trying to tell me how people use the language, not necessarily that it's your decision.
But I have decided that I'm going to use that.
Okay.
because I want people to understand me. Yes. So
okay. So but there's also the difference between deciding that you're going to use it versus how you would have decided if you were in charge of everything. Okay. So again, I'm already learning lots of things here, but I'm not sure if you or anyone else can get anything from what I'm trying to say here. So let's see. So okay. So that's already really interesting. But I'll really have to think about what the generality is of these things and how much difference it could make. So I mean, from things you said, I mean, might have misinterpreted what you said, but from things you said, it's like you're suggesting to me the possibility of something that I had pretty much ruled out. And, you know, now you got me wondering whether I should have ruled it out. So, you know, I think that unless I've really screwed up, there's a completely straightforward one-line proof. Not that I can remember what the one line is, but there's some completely straightforward one-line proof that says that if you have an invertible object in a Cartesian monoidal category, then it's the terminal object. So you don't get any line objects in Cartesian monoidal categories. And, you know, so I've got this naive argument that says, well, Frobenius algebras, special commutative Frobenius algebras don't form a Cartesian monoidal category, but separable commutative algebras do, I think. Sounds like from what you're saying that separable commutative algebras form a Cartesian monoidal category. So
the invertibility only comes in when you go to extra special, right?
Yes, but we're saying that in the Cartesian monoidal category of special commutative, you know,
yeah,
I might be screwing up in all sorts of ways, but at the moment I'm thinking that, and now I am using your terminology about the difference between separable and special commutative Frobenius. So, you know, when you're dealing with separable commutative algebras, then you really are dealing with these more general morphisms. So you're getting, yeah. I mean, what am I trying to say? A commutative algebra.
You're getting a Cartesian category. I think if you take the op of the category of separable algebras, then it's Cartesian.
Right.
And then
and therefore the invertible ones are just terminal. And a more mundane way of saying this for a lot of people is just to say that what am I trying to say? A commutative, I hope I didn't screw this up. A commutative algebra the underlying module of a commutative algebra is never invertible. Is that what I'm claiming? So a commutative algebra has an underlying module, and you can ask whether that's invertible. And when I say it's never invertible unless you are the algebra itself. So you know, you know, unless you are the base ring itself. You know, right? So, right, the base ring itself, that's the geometrically terminal. That's the initial, you know, algebraically initial or geometrically terminal thing. And unless I'm screwing up, that's what I think I'm saying. And I mean, and that would be true for just, you know, I think that would be true for just for the commutative ones, but even more so for the separable commutative ones. So I don't know, because okay,
I think all this is right. This all sounds right. Yeah. But
it sounded like you were saying something, because it sounded like you were suggesting that there is, right? So it's like I almost seem to be suggesting that the extra special ones are just too extra special to even be useful. Because it's like I'm claiming that they're really just I was going to say that I'm claiming that they are the algebras where the unit morphism is invertible. So
yeah, that's what the extra, yeah, and in fact, the extra law
yeah.
that makes a special thing be extra special. That just says that the unit has
Unit and co-unit, unit and co-unit
invertible are each other's inverses, yeah.
Are inverse to each other.
Yeah.
Okay, in
so
a way
that
that does
right away if you start from that.
Okay. So that is all fitting together. But it still makes me wonder what, it almost makes it seem like what I said, that the extra special things are just so, they're so hothouse flower that, they're just trivial in some sense. So I'm not sure why people would even want the terminology, but maybe just, I don't know, maybe it's a handy terminology to have sometimes. Okay. For a moment, you had me thinking that, there was some sort of twisted version of an extra special thing, but I guess there's not. Okay.
That's a good point. I never thought about that, but I think there isn't. Yeah, at least in the.
Okay. Okay. So, okay. I am rambling on here. So, but rambling on, which means that, I really am aiming to quit at the right time here. So let's see. So I should try to get to the point here. I should try to get to some point here. So let's see. So, what am I trying to say? Well, okay. So one point I was trying to make originally was that, there is something attractive about the syntax of the special commutative Frobenius prop, which is that you can say, what the operations are. They are cospans of finite sets. And as opposed and I was calling that a global viewpoint as opposed to the viewpoint where you just present a prop by generators and relations. But so one of the things this suggests is that this theme that a lot of these other Frobenius props have that flavor too, that you have this sort of nice global picture of the syntax of these things. So there is some version of a Frobenius prop, or I'm not sure how commutative it is yet or anything like that, but there's some version where, it's less special, but where the syntax is more like not cospans, but something related to cospans. In a way, it's a special kind of cospans, which is cobordisms. Think of cobordisms.
Yes, those are the commutative. I'll give it away. Those are the commutative Frobenius algebras. Commutative Frobenius monoids.
Well, okay, but there are various. Do you know if that was in the chart that we were staring at?
No, that was not in the chart.
Because the chart was more combinatorial flavored stuff, I guess. So, okay, but of course, right? There's already things we can have. You kind of just gave an answer or something like that. That the cobordisms correspond to, I guess you said, commutative Frobenius or something like that.
Yep.
But that that doesn't completely answer all the questions for me, because, and not even the questions just about that, just because of the fact that, to me, there's all sorts of slightly different versions of cobordisms. There's totally framed cobordisms, totally unframed ones, and then a whole vast spectrum in between.
So I don't know how vast it is in the two-dimensional case, but anyway, but it's not empty. So I'm an oriented cobordisms, two-dimensional cobordisms are giving you the commutative Frobenius monoids. So it's true that you could ponder the unoriented cobordisms.
Have you thought about that? Because my friend Simon has thought about that, and we actually talked about that, and there's something interesting about it. I might as well throw it in. I might as well say something here. So, do you have any interesting to say about that right this second?
Not right this second. I have thought about it, but
Okay, well, one interesting thing about it, I mean, we didn't completely clarify it, and we kind of made stuff up and read what other people were saying and stuff like that. But apparently there's something going on there. It's kind of like I want to say something like can you is there any possible way that anybody can remember whether B series is symplectic and C series is even dimensional orthogonal or vice versa, right? It's hard for me to remember the difference between B and C, the B and C series of Dinkin diagrams.
B is orthogonal and C is symplectic.
You're really sure about that?
Yes.
Okay, okay.
I don't know why I'm so sure, but I just know it.
Okay, I'll go along with that for a second. For the moment, I'll go along with that. So
what are you up to?
So it turns out that, I mean, right, I've been claiming that, right, my original viewpoint when you started talking about special commutative Frobenius algebras, I started just relating them to n-bang torsors.
Uh-huh.
N-bang is the A series of Weil groups for Dinkin diagrams. But so there's a variant concept of special commutative Frobenius algebras, and some people might call them unoriented, or some other people might call them symplectic or something like that. But the point is that the unoriented ones are sort of symplectic in the sense that, what you end up working with instead of the A series Weil groups, which are just the symmetric groups, you end up working with the C series Weil groups, the symplectic Weil groups, which are, just some semi-direct product, right? It kind of makes a little bit of naive sense because you've got this extra involution thing going on, and that somehow has to do with reversing orientation or something like that. So
the link between the Frobenius algebras and A series, or the commutative Frobenius algebras and the A series is, I understand it so poorly, I can see how to do other. I know you've said they're connected to n-bang torsors, but I don't.
Well, but okay, but let me try to give you a little bit of propaganda for it by throwing back at you something you've been emphasizing to me, which is you've been emphasizing that the homomorphisms of these things are isomorphisms. So that, right, that sort of isolates the different cardinalities from each other. And at that point, you kind of are dealing with, if you right, so you can talk about a
cardinalities meaning dimensions or what? I mean,
yeah, roughly speaking, yeah. I mean, you make it precise, but so there's right. We talked about it in terms of these prop congruences. There's this ladder of prop congruences, and they correspond to really the dimension of, in some sense, or right. I mean, you can call it dimension or you can call it cardinality, right? I mean, it depends on whether you're thinking of the underlying vector space of the Frobenius algebra, of the special commutative Frobenius algebra, or you're thinking of the idea that it's morally a finite set, so morally it has a cardinality. And so you can you can just say where you are on the ladder of these prop congruences, and at that point you're basically dealing with n-bang torsors. I mean, there might be a little bit of imprecision in what I just said because of the fact that when we looked up, people's concepts of, I mean, there was this thing where people, when they were talking about special commutative Frobenius algebras over commutative rings instead of over fields, then they started imposing like flatness conditions and things like that, and that was like something we didn't really want to think about it, and we still don't want to think about that. But nevertheless, so I'm saying if you focus on a particular cardinality, so to speak, of special commutative Frobenius algebra or cardinality of its spectrum, then then you should be able to, by the idea that, special commutative Frobenius algebras have a lot to do with n-bang props. Whereas the unoriented version has to do with these. Did I say the right word? Did I say n-bang torsors? Is that right? Did I say the wrong word? N-bang torsors. And whereas in the unoriented case, you're dealing with the torsors of this semi-direct product. I think it's something like the semi-direct product of 2 to the n acting on, no, n-bang acting on 2 to the n or something like that. Yeah, I just wanted to throw that out there. There's something possibly fun going on there, but there's things I don't understand about it. Like one of the things I get confused about, let me complain about this. One of the things I get confused about is that when people start talking about unoriented topological quantum field theories or something like that, or these unoriented cobordisms, I get a little bit confused about whether the unorientedness is, to what extent is it applying just to the objects versus to what extent is it applying to the morphisms? Because, there's funny relationships between orientation of the boundary and orientation of the manifold itself. So I get confused about that. Anyway, also I do get, well, let's see. So okay, so let's see. So let's see. So okay, so let me try to write down something you said, which is that commutative Frobenius. And again, I'm suggesting that for me, I need to eventually clarify some of the fine print in this. But you're saying the commutative Frobenius prop relates to, you said oriented cobordisms?
Yeah.
No, yes, oriented cobordisms. Oriented cobordisms between one manifolds, which is possible, people may emphasize the 2, which is the morphisms or something, but it's the one-dimensional manifolds that are the objects, right?
Yep. And they treat those as oriented as well.
Say that again. What's oriented as well? The
one-dimensional things. So oriented cobordisms between oriented manifolds. So that's just what the people.
Yeah. I just for a moment I was, well, okay. There may be other ways to say it too, but that may be a good way to say it. Okay, so I'll just say oriented one manifolds and oriented 2 cobordisms. All right. Now, do you think, it sounded like you may be suggesting that framing is first of all, are you suggesting that orientation is a special case of the intermediate framing here? It may very well be. I'm a little disoriented at the moment. Yeah.
Yeah, it is in general, but I'm not. I forget now. Let's see, in this 2-dimensional case, how much room there is between the 2. They might be the same for all I remember. So when people talk about framing, they always mean a normal framing, a framing of the stable normal bundle. That's
well, yeah. I was right. I was suggesting that you were suggesting that framing is going to be relatively trivial in this low dimensional case or something like that. It's not going to obstruct things too much or something like that.
I think it might be the same as just orientation in this case. In 3 dimensions, it becomes, that's when people start talking about it. So I think that maybe that's when it becomes stronger than just orientation. But I'd have to think about it to see if it's really what I'm guessing is really true.
Okay, so I will consider this a victory if, right, because I got 5 minutes left. So I will consider it a victory if I just manage to get the following sentence out, if I can remember what the following sentence is. So it's not really the following sentence, but I'm about to try to get to. So what am I trying to say? That what am I trying to say here? So can you repeat what you just said? That'll help me remember what I was trying to say. Yeah.
That orientation and framing might be the same in 2D,
okay.
definitely not in 3D.
Okay, well, so let me think for a minute here. Let me think for a minute. What am I trying to say? So, orientation, framing. Right. Okay, right. Okay, right. So there's right. I've been saying I have naive questions. I want to state my one really naive question.
Okay.
And I am putting these conditions on it. Don't tell me the answer right away. I mean, in fact, we may run out of time before you can even have time to answer it. But,
okay.
So let's focus on this case that you're talking about here, what you're calling a commutative Frobenius problem. And you're telling me that syntactically, it's this cobordism category. Cobordism category in the sense that the morphisms are cobordisms.
Yeah.
Yeah, don't tell me the answer. I'm very unclear on to what extent the cup and cap stuff just automatically in this context give us a non-degenerate pairing. That's what I'm trying to clarify. So yeah, that's what I'll have to think about when I go home. But it does sound like you're telling me that I should be able to figure this out for myself from what you've just said. If I think about it carefully enough, I just have to stare at the cup and cap. Well, I have to figure out what cup and cap mean when you have orientations and stuff like that. Because I'm getting a little bit confused about orientation, right? I mean, so like, what am I trying to say? That I mean, I think what it should just mean is, having a non-degenerate pairing should basically just mean that category theoretically, we have an adjunction. We have an object having an adjoint. Now, in a prop, the way we're doing it so far, just a plain prop, there's basically just one type or one generating object.
I mean, a pairing is an object is its own adjoint.
That's you didn't let me say. That's right.
Okay,
actually no. I think I disagree with that. I think I talk about.
No, I don't agree. Yeah, going too far. But I mean, but it's not just an adjunction. Sorry.
Yes, but I'm still. But okay. But what I was trying to say was that in a prop, you only have one type, so you don't have much other places to look for an adjoint, other than using the object itself for an adjoint. Now, of course, you can play games where you have multi-type props, et cetera.
Okay, fine.
And
you weasel a lot of that one. Okay.
Okay, and right, and okay, but then you also right. There's a lot of weird possibilities here. I mean, for example, and now I'm getting mixed up between, level slips about commutativity. So you could have, commutative Frobenius algebras, but you could also, you could have like a non-commutative prop or something like that, which is perhaps called a pro or something like that. Or you could have a prob. Do people talk about probs?
Very little, but yes. They do.
So in other words, the P at the end of prop stands for permutations, if I'm remembering correctly. Is that right?
Yes, it does.
So a prob sounds like, it's funny, I don't remember anybody saying this, but
people do. They do, but very rarely. I'm like,
shouldn't we get them to say it more? Because I don't know.
Well, they need
I mean,
examples
they
of,
don't, people don't even say prop that often, but what are you saying? Yeah.
they just need more examples that they're really interested in than else.
Well, there might be some. Okay, but that's interesting, the idea that they need more examples, because I have a feeling there should be examples floating around here. You don't think so?
Probably.
Uh, all right. Oh, okay. We're really going to quit here, but right now I'm just summing up here. So okay. So I like I said, I kind of as a victim. I did state my question. So but right, the point is I have to go home for homework, and I really have to think about what you're saying here.
Okay.
I really have to think about this cup and cap. Oh, I was going to say right. I was going to say that right. I mean, if you start maybe having non-commutativity at the algebra level or non-commutativity at the macrocosm level, you know, like braiding at the macrocosm level or something like that, then at some point you're going to run into this idea of ambijunction, where instead of having an object being adjoint to itself in a completely symmetric way, you can have it be adjoint to itself, but in this funny braided way, right? Braiding, it's I think it's sort of in a braided way, you know, because you get, you know, it being left adjoint to itself and then being left adjoint to that again doesn't give the identity or something like that. So I think that gives some sort of twist, somehow gives a braiding or something like that. So there's things like that going on. Let's see.
Yeah, there are things, by the way, called symmetric Frobenius algebras, which don't need to be commutative. Sorry, but where there's some kind of symmetry of the pairing. So anyway, that may be like not quite what you're talking about, but it's like yet another thing.
All right, I'll just put it on my list of things to learn about. So symmetric Frobenius algebra. Okay. So I think I'm done, but I'm just thinking about whether I'm done. Let's see. So yeah, I stated my right. Well, okay. Yeah, let me just for my punchline, so I can pretend that I'm done, is I just want to state what my homework is in terms of what's bugging me. So what's bugging me is I can picture this I can picture some sort of cap-like cobordism in the context that you're talking about, and I can picture some sort of cup-like cobordism, but I really have to think about, you know, to what extent does it parse in such a way that you can put them together to get the triangular identities and stuff like that. So
no, it's
or you know, whether you can do it both directions or you can only do it one direction, and you get I have to really think about that.
Yeah, and you have to think about whether those circles that are the boundaries of the cap and cup, pairs of circles, how they're oriented. If you want to use oriented cobordisms.
Yeah, yes. We already hinted about that. But another thing you have to think about is this whole sort of motivating picture of, I guess in some sense, this is basically what string theory is about, right? There are these string diagrams that you may use when you're describing, sorry, I shouldn't call them string diagrams. I should call them
particle diagrams. Well, people call them
diagrams. But wasn't there a name for
confinement diagrams?
But isn't there another name for it? I mean, because you know, after you stringize this thing, it's going to become a trinium or something like that.
Trinium, yeah, that's called a trinium.
And if you really want to functorialize this process of turning this, what's the name for this? It's not a triskelion. What do I call it? A tripod. Let's call it a tripod for a moment. If you want to really nicely functorialize this process of turning a tripod into a trinion, then you probably want to do it in a three-dimensional context, right? It's like, right? I mean, it's because you know, well, I mean, or there's something Tom Pontriagan-ish going on here, or something like that, right? I mean, it's like the territorial waters of a country that's shaped like just this, you know, one-dimensional thing. Is going to stretch out to give you a solid trinion. and that's going to functorialize this process. And but the surface, the surface of the trinium, the surface of the solid trinium, that's a two-dimensional surface, and it's like a string diagram instead of a particle diagram. So, but that 3D thing, that's suggesting that this should be a prob instead of a prop. So sorry. I need to go home. I need to go home and think about this. So thanks a lot, and I'll try to see you next week.
Okay, doke.
Okay, thanks.
Yeah, I'll see you.
Okay, bye.